Okay, good morning, ladies and gentlemen. Thank you very much for attending the webinar today on this fine Wednesday morning, February 20th, 2019, and looking forward to discussing AFT Arrow with you all. Little disclaimer, I'm feeling a little bit under the weather this week, and so bear with me, just kind of try and pull through this as best I can. If all of a sudden you hear me go mute, just wait online for a few seconds. It probably means that I need to blow my nose or something. So hang with me, and that way if I'm out of sound for a few seconds, you'll know what's going on. All right. So I have, for those of you who are listening in live, this webinar is being recorded. That way you'll be able to watch it again later on at your leisure, or you can send it around to your colleagues so that they can watch it as well. Also, the webinar is being recorded for later viewing, so for those of you who are listening into the recording, if you would like a copy of my presentation, which is very, very basic, feel free to email me, benkeiser@aft.com, and I'll be happy to send it to you, benkeiser@aft.com, and I'll send it over. For those of you who are listening in live, it is included with the handouts that I have provided for you. So that way, for those listening in live right now, you've got my presentation already. Okay, so I'm going to go ahead and jump into this. Today I'm going to talk about how to account for compressible effects correctly and why you need to use AFT Arrow. The first couple of slides right here, I'm just going to skip through. This is some boilerplate stuff that you can keep on hand for reference. This is just all the different things that you can do with our software. And this is a summary of each of our software products, Fathom, Arrow, and Impulse, Mercury, Titan. We've got some utility products. All of those are available, and you can find out a lot more information on our website. If you go to aft.com, you can find information about each of our products down here. So I'm not going to spend very much time on these two slides. I'm just going to jump right into it, which I'm pretty sure that that's what you all have been waiting for. All right, so what's so special about compressible flow with dealing with gas piping systems? Well, this is the mass flow rate equation. The mass flow rate equals the density times the cross-sectional area of a pipe times the velocity. In incompressible flow, your density and your densities and velocities are constant, therefore your mass flow rate is very easy to calculate. However, when you're dealing with compressible flow, your density changes are significant as the gas expands when it flows down a pipe. And in addition to the density changing, since the area is going to be staying constant, the velocity would have to change in order to compensate for that. In addition to the velocity changing, it's typically a nonlinear change in velocity, and you'll see how the gas accelerates along the pipe, and incompressible flow methods will not account for that. Your density change is not only dependent on temperature like it is for liquids, but there's also a pressure dependence that's important to account for now, and that flow rate is coupled to the energy balance and equation of state. You can potentially have sonic choking if your gas velocities are reaching the speed of sound. Sonic choking can also become a dominant characteristic of your system. You can have multiple choke points throughout the piping network of your system. And ultimately, all of the governing equations that are solved together are strongly coupled together, and they need to be handled properly in order to correctly account for gas flow. So here's some basic methods or different methods of analysis that you can work with. One of the most easiest ways to model compressible flow for gas piping systems is to simply use incompressible flow methods. That would be like if you were using AFT Fathom to model your gas system. This is very, very robust and highly inaccurate. It will require large safety margins. Sonic choking is not even considered, nor are you able to handle heat transfer or elevation changes or real gas effects. It's a very, very, very simple solution, just to give you a very quick idea of what you might see, but who knows if the results are correct. That's the issue, is if you're using incompressible flow methods, you're never going to be certain if your results are actually good or not. There are some various compressible flow correlations that are available, and a lot of them only deal with either isothermal conditions or adiabatic conditions. They completely ignore heat transfer or real gas effects. They really are only valid for one single pipe at a time. You can't really extend them to large piping networks. They don't handle sonic choking. And again, you can never be sure if the answers are actually correct or not. So again, those compressible flow correlations that are simplified sidesteps really just fall short of getting the job done. Incidentally, AFT Arrow actually has a couple of these compressible flow correlations built in. There's the Weymouth equation and the panhandle equation. And so if you open up the pipe property window when you're in AFT Arrow and you change your friction model to Weymouth or panhandle, that's how you can use these correlations for the pressure drop in the pipes. But again, they are significantly simplified methods. Lastly, there's the good old-fashioned in-house iterative spreadsheets that people use. Those are typically based upon either the simplified correlations or maybe they're just assuming incompressible flow. Again, they typically do not handle real gases. They're going to have to simplify and use ideal gas behavior and also sorry, my phone rang. I was getting distracted there. I apologize. Turn my phone down here. There we go. So they simply do not handle real gases. They take into account very large assumptions and are very prone to typos in equations and spreadsheets. And so that can be a real issue. And a lot of times those spreadsheets are developed by non-compressible flow experts. So overall, the problems with these traditional methods, typically you're going to be assuming ideal gas behavior when gases are highly non-ideal. Another assumption is to assume isothermal or adiabatic conditions, and a lot of times you're going to have heat transfer impacts that help or that make an impact on your flow distribution. And so a lot of times the belief is that the analysis is better than it really is. And so you also have a difficult time handling parallel flow networks. So when you're dealing with those traditional methods, the answers are typically not as good as what you might think they are. Now, here's what AFT Arrow does. AFT Arrow includes all compressible effects. So it will handle heat transfer, real gases. It can handle sonic choking throughout the network. It will be able to handle complicated piping networks, not just single flow path systems. And it's got a very powerful solution engine built in that will handle compressible effects properly. This is a really awesome technical paper that Trey Walters, the president and original founder of AFT, wrote for Chemical Engineering Magazine back in 2000. And even though 2000 is 19 years ago, the concepts are still incredibly valid today. So thermodynamics has not changed, all right? that technical paper will give you a very good comparison between the various traditional methods that have been used and how it's really important that you use fundamental thermodynamics to handle your gas piping systems. And those equations that you'll see in that technical paper are what are built into AFT Arrow. And I'm going to talk about that today. So these are the 5 fundamental thermodynamic equations that AFT Arrow is solving. We've got the mass balance, momentum balance, energy balance, equation of state, and Mach number equation. And as you can see, for the momentum balance, we have our gravitational term in there. And so we are properly handling elevation changes in gas piping systems. And all of these equations are significantly coupled with each other, and Arrow is going to solve the mass, momentum, and energy balance as the gas travels down the pipe. And they are solved simultaneously with each other. Now, I'm not going to spend time today talking about the different solution methods that are available in AFT Arrow. So if you were to open up the AFT Arrow help file, you can go to the help menu and then contents and index. And this is where you can find information about that. So if I go into the solution control window, the first tab that you see here is the different solution methods that you can work with. I would recommend using Arrow default as much as you possibly can, because the default solution methods and tolerances are going to solve about 99% of your cases. Rarely will you ever need to change solution methods or tolerances. So just stick to Arrow default and that'll do the job for you. However, it is important to understand how Arrow is solving the fundamental thermodynamic equations throughout the piping network. So if you open up the help file, I just want to make sure that you all are able to see the screen that I'm seeing here. And so, yep, good. So if you were to go in here to solution control, or actually it's theory and references, this is where you can read through a review of compressible flow theory. This is very valuable. And then for solution methodology, here's where we can talk about the various marching methods, fundamental equations. So if you go to compressible flow theory in single pipes, here you can go to the related topics for the length march. This is the full-blown derivation of the length marching method that we are using. Similarly, you can read about what the Mach number marching method is. So if you read through those topics, you'll have a much better understanding of what those solution methods are actually doing and how AFT Arrow is properly handling all those complex thermodynamic equations. Now, something else that I want to talk about is heat transfer. It's a common belief that people will use is assumptions where adiabatic and isothermal conditions will bracket all potential flow cases that you might encounter. And that's simply not true. It really depends on what your system has going on. And so this is a very simple example here where we have 4 individual piping systems, and we have an adiabatic case, an isothermal case, a case where the gas is heated down the pipe, and then the case where the gas is cooled off down the pipe. As you can see from the results, based upon the pressure drop is constant. We've got a known pressure at the inlet and outlet of each system here. Based upon the temperature profiles, you can clearly see that the adiabatic and isothermal flow assumptions are not bracketing all potential temperatures that you might see throughout the network. So this is what you would see if your gas was heated or if the gas was cooled. So that's one area where the assumption of adiabatic or isothermal flow is not good enough. Okay, if temperature of your gas is an important parameter that you care about, then you need to be sure that you handle your heat transfer calculations properly, and Arrow will do it for you. In addition to temperature profiles, the heat transfer also will have an impact on your pressure and flow distribution. Here I have constant pressure drops in each of the pipes, so my flow rates are going to be different. If you look at the flow rate results here for each of these cases, what you would find out is the case where the gas is heated up, that produces the lowest mass flow rate out of the 4 systems, followed by the case where the gas is cooled, that's the highest flow rate. So again, simply assuming adiabatic or isothermal flow will not bracket all conditions. You need to account for your heat transfer properly. In addition to heat transfer, compression thermodynamics is also important. So as you compress a gas and increase its pressure, like across a fan or a compressor, then you will have a temperature increase across that device. And so these are the equations that are being used to determine what your outlet temperature is on the downstream side of a compressor. Now, this piping system right here that I have shown is one of our standard examples in AFT Arrow. The picture that I've displayed here is very slightly modified. So if you go into AFT Arrow and you open up the help menu and then go to show examples and then expand the walkthrough tutorials, it's the air blower sizing system. So as you can see, this is the example that will show you the effect of compression thermodynamics and how that will change your temperatures. And there's 4 different cases in that example that is discussed. It has you assume a adiabatic case, so where your efficiency is 100%, followed by an 80% efficient compressor, 60%, 60% with heat transfer, etc. And what you'll find is that the temperatures increase dramatically. These are the results of that piping system. And so if you focus in on the results here, I've highlighted the resulting temperatures in degrees Rankine, but I also displayed them in degrees Fahrenheit. So here we have a fairly constant temperature coming into the compressor or into the blower, which is right around 70 degrees Fahrenheit. The temperatures that are coming out of the blower or compressor are shown by these values. So if you are assuming an adiabatic compression process where you have a 100% efficient compressor, you're still going to have a significant temperature rise. It's jumping from about 70 degrees Fahrenheit up to 160 degrees Fahrenheit. So that's a very large temperature change. If you're using one of the compressible flow correlations or incompressible flow methods to handle your system, it's not even going to account for that at all. And so your temperatures will just be constant and completely wrong from what you would see in reality. As you decrease your efficiency, you can see how your temperature dramatically increases. So for a 60% efficient compressor, we have an outlet temperature of 230 degrees Fahrenheit. So very important to account for compression thermodynamics just as much as it is to account for your heat transfer cases in general. Now, I'm going to go ahead and jump into the software at this point, and what I want to do today is I want to do a comparison using both Fathom and Arrow. So this is the standard example from the examples help file that I showed in the previous slide here. However, I have slightly modified it. The mass flow rate here, I'm just using a very simple mass flow rate of 2 pounds per second. And what we're doing here is we are taking in atmospheric air, and then we have a blower, and we're distributing that air to several different rooms. So this might be a simple ducting system for a building, perhaps. Now, as you can see here, my pipe sizes are not very large. I start off at 6 inches in diameter, and then I go down to 4 inches in diameter, and then each of the branching points here are 2 inches in diameter. But you can see that you have some decently long pipe lengths here. And so the question is, if you were to try and model this type of system, since it's just using air, if you were to model this in Fathom, how good will your results be? Or if you were to use a compressible flow correlation, how accurate would your calculations be? So what I've done is I have modified the standard example in Arrow, and then after I built it, or I modified it in Arrow, I imported the model into Fathom, and I modeled essentially the same thing. So let me go ahead and jump out of the slides here, and then I'll open up the AFT Arrow example. So here's AFT Arrow. Let me open up my model really quick here. Let's see. That's the one I want. All right. Okay, so now that I have this open, what I've done is I've slightly modified the scenario manager. I'm only looking at the 80% and 60% efficient cases. I'm not paying attention to the adiabatic case in this particular comparison today that I want to do. So those are the only two scenarios that I actually care about looking at. Also, I deleted the subcase of the 60% efficient scenario where I was accounting for heat transfer. So I removed that. So when it says adiabatic, it's talking about an adiabatic compressor where it's at 100%. Each of the pipes are using a adiabatic heat transfer model, so they're not losing any heat to the environment. So I have my atmospheric air, which is coming in at 0 psig and a temperature of 70 degrees Fahrenheit. And then through my blower, I'm going to try and size my blower. It's operating at 2 pounds per second, which if you were to read through the example help file model, it uses a different flow rate. It uses a flow rate of 1,330 standard cubic feet per minute. So I simplified it just a little bit further. Okay, so what I'm going to do is I'm going to jump to my 80% efficient scenario. All right, so that's loaded. Each of these rooms are operating at 0 psig, so essentially I'm just discharging into atmospheric conditions in all those locations. So in order to account for the efficiency of the blower, when I open up my blower or my compressor here, as you can see, I'm using the sizing option for a centrifugal compressor. You can also do a fan option. And I'm going to, for the compression process thermodynamics, I'm using determined from efficiency data. Now, if you had a compressor curve or a blower curve, you could specify that here, and then you can model your efficiency changing as the flow rate changes. But here, I don't have a curve yet because I'm trying to size my fan. So I'm just doing a very simple case where I have a fixed flow rate of 2 pounds per second and a nominal efficiency of 80%. Okay, so let me go ahead and go into Fathom now. Now, the way that you would import a Arrow model into Fathom is very easy. One of the biggest benefits to using our software is when you know one of the products, you know how to use the other ones. The interface is virtually identical. So if you know one of them, you know how to use the others. There's a lot of cross knowledge that you can take advantage of. The other significant advantage is that you can import any AFT model across any AFT product. So if you have an Arrow model that you've already built and you want to bring it into Fathom, you can easily do that. So here, what I would do is I would go to File and then Open. And what you would do is you would change the file type to all. And when you change the file type to all, you simply browse to wherever you have your arrow model saved, which in my particular case would be in this folder right here. And if I sort by type, I would select one of the arrow models and then just click Open. And that's how you would be able to open up a fathom or an arrow model into AFT Fathom. Now, I've already done that. I'm not going to do that here, and I've already set up my models accordingly. So I just need to open up the Fathom model that I already imported from Arrow. So this is my Fathom model right here. And there we go. So as you can see, it's the same system. However, there are some slight modifications that you might have to make when you're bringing an Arrow model into Fathom, or a Fathom model into Arrow, or a Fathom model into Impulse, etc., etc. About 95% of the information will be transferred over, no problem at all. But one of the key differences between Fathom and Arrow is in Fathom, when you are selecting a fluid with the System Properties window, you have to specify a temperature. Now, if you're trying to model a gas in AFT Fathom, which you do have the ability to do, we've included some gases for you. So I'm modeling air at 1 atmosphere, and this is my temperature reference. So what this is going to do is it's going to use 70 degrees Fahrenheit in order to calculate the density and viscosities in each of the pipes. This is temperature dependent only. So if you're modeling a gas in Fathom, it's not going to pick up your changes in density or viscosity from functions of pressure. That's because it's assuming incompressible flow. In order to handle that correctly, you need to use AFT Arrow for that. But again, the question is, how good would Arrow do being able to handle this? If you had a better idea of how your temperatures might be changing through the system, as you can see here, you're not allowed to model heat transfer for your gases in Fathom. That's because, again, Fathom is modeling incompressible flow, so you do not have the ability to model heat transfer. It's going to limit you to isothermal flow. Now, if you have an idea of how the temperatures are changing in each of your pipes, you could get a little bit closer by using variable fluid properties. So if you know how your temperatures are changing, you could say these pipes are 70 degrees, maybe these pipes are 100 degrees, these pipes are 120 degrees, etc. And that way you can get a little bit more accurate of density and viscosity calculations inside your pipes. So that would get you a little bit closer. So that's one of the key differences is you have to specify a temperature for a particular gas, and Fathom is not going to account for compressible effects at all. So that's one thing that I had to update when I opened my Arrow model into AFT Fathom, is I just had to go in here and I had to select Arrow as my gas, and I had to specify a temperature and calculate the properties. If you look at AFT Arrow, let me close the help file. If you look at AFT Arrow, the system properties window is a little bit different. All you need to do is pick a fluid. That's the only thing that you have to do in Arrow. The reason why is because your conditions are established at your boundary points. So here's where you specify your pressure and temperature boundary condition, and then your pressures and temperatures will change accordingly with relation to the various governing equations that are built in. The next thing that I had to do is, if you were to open up the help file example for the air blower sizing system that we've provided for you, you would actually not see 2 pounds per second. This is one of the things that I changed right here. Originally, the standard example has you modeling standard cubic feet per minute. And I think the value was like 1330. So that was something that I needed to change when I imported my Arrow model into Fathom. Now, the reason for that is because when you have the flow rates of, or if you have a volumetric quantity, standard cubic feet per minute, or perhaps normal cubic meters per hour, those volumetric flow rates, when you have the words standard or normal in front of them, it ties that volumetric parameter to a specific density of a gas at standard temperature and pressure conditions, or normal temperature and pressure conditions. So that's why if you have standard or normal and then the volumetric quantity, it's considered a mass flow rate, not a volumetric flow rate. So if you want to do standard cubic feet per minute, what you would need to use is mass flow rate as your flow parameter. And then in your drop-down menu, you would change your units to SCFM, or perhaps you might be using normal cubic meters per hour, for example. So what I had to do when I imported my Arrow model into Fathom is I had to make an adjustment. So here's my Fathom model. What I did was in my base scenario, I went into my fan, which in Fathom is a pump, but again, I still had my sizing options selected, but for my mass flow rate, if you look in that option here, there is no SCFM. There is no standard cubic feet per minute. That's because this is incompressible flow. So if you wanted to model volumetric, you would use volumetric and then do cubic feet per minute. But here's the thing, is that this value is not the same as using standard cubic feet per minute in Arrow. Those are going to be different, and you're actually going to see that in the results that I'll be presenting to you for the examples here. So when I brought this into Fathom, so what I did was when I opened my Fathom model, the first thing I did was I went back into Arrow, I ran the model, and I calculated what my mass flow rate was as more of a fundamental quantity, like in pounds per second, instead of standard cubic feet per minute, or whatever it was. So once I figured out that it was around 2 pounds per second, I specified that directly here. Now the base scenario assumes a 100% efficiency. So if I went to my 80% efficiency system, this is where you see the percent for the efficiency. Now, the other thing I had to change was when you're in AFT Arrow, we have the tank junction, which is this type of junction right here. All it is just a pressure and a temperature. That's all you're specifying there. However, when you bring an Arrow model into Fathom, it will initially import it using a reservoir junction. A reservoir junction in Fathom, you have to specify a liquid surface elevation. Well, with this being a gas system, there is no liquid surface elevation. So what I needed to do was I had to change my reservoir to an assigned pressure junction. So that's why you have an assigned pressure right here. And all I did in that system was simply open this up here and I specified 0 PSIG. Now I don't have a temperature specified here like I do in Arrow. The reason why is because in Fathom, I'm specifying my temperature in the system properties window. So 70 degrees Fahrenheit, that's all that it's going to be. All right. So now what I'm going to do is I'm going to go ahead and do a batch run of the 80% efficient and 60% efficient scenarios for Fathom and Arrow, and we'll compare the results. So let me go ahead and do that really quick. So in Arrow, I'm going to go to File and then Start Batch Run. And if you click on Add Scenarios, this is where you would add which specific scenarios you want to run in a batch mode. So click OK, and then I'll start my run. And then I'll do the same thing in Fathom here in just a sec. So this runs the first scenario in Arrow, and then it runs the second scenario. All right. So here are my results for the 80% scenario in Arrow. I'll come back to that in a sec here. And then let me go ahead and do a batch run for Fathom. So I've already got my scenarios added, so I'll do my batch run. Now, while that's running, I want to do a really quick side note. I was talking about standard cubic feet per minute and normal cubic meters per hour, and so a lot of that can kind of get confusing. And so if you were to go to our website, AFT.com, I'm pulling that website up right here. Give me just a sec. So if you go to AFT.com, under the Learning Center for webinars, this is where you can find all of our upcoming webinars. So you all are in this webinar, so you should all know how to find that. But if you go back and then under webinars, go to the webinar library, you would have to fill out a quick form. I've already filled out the form, and then you have access to our webinar library. All of these webinars that you want to watch that are recorded are available for free. So you just fill out the form, and then you'd be able to access this page here. So if I go to AFT Arrow, there is a webinar that I did last year back in, I think it was July. And this was the webinar that I did called A Study of Dust Collection Issues. And for dust collection or ducting systems, a lot of times people will use standard cubic feet per minute or normal cubic meters per hour or actual cubic feet per minute. And so if you were to watch that webinar, I actually give you a breakdown of how those different parameters are different. And if you remember to email me, then what I will be happy to do is if you watch that webinar, then I'll be happy to send you a copy of my presentation I did for that webinar. And it contains the discussion that I did on actual cubic feet per minute. And where did I talk about it? Here it is. So as you can see, there's a lot of differences there, and I'm going to show you those results today, and it's going to highlight why this is confusing, and it's also going to highlight why even if the results are fairly close between Fathom and Arrow, it just goes to show how incompressible flow methods just leaves things completely uncertain as to the results that you would actually see in your system. So email me, watch that webinar, and I'll send this presentation to you. All right, move that out of the way. Okay, so here's Fathom. Let me go back to Arrow. So in Arrow, these are the, well, if I went to the output control window and then click on Arrow Default, this is how you would see the default output parameters structured for your Arrow results if you first went to this page and you didn't choose anything. I already went through and I customized my output. What I did was I opened up my output control window, and I basically went in here and I removed a whole bunch of parameters, like name of the pipe is just called pipe, I don't care. I removed the Mach number. I removed a whole bunch of stuff. I added some things. I took out the enthalpies. And what I did was I clicked, after I set up everything here for all the different parameters I wanted to show, I reordered things how I want them to be arranged. I set up the units that I wanted to use. After you do all of that, if you want to have a consistent reporting format for all of your different models for you and your colleagues, what you can do is arrange it here and then click on Save Control Format. And I've already done that. You just give your control format a name, and it's going to have the extension DAT. That's a database file. After you create your control format, if you want to use that same format of output results in other model files so you don't have to keep changing it over and over again, simply click on Load Control Format, and then you can browse to where your control format files are. Here's my one for Arrow, and I can open that up, and then bam, look at that. It contains all of my results for me for how I set things up. As you can see here, I'm showing my units for pressure in terms of PSIG. So now when I click OK, that filters out my output just like how I want. So this is the results for my 80% scenario. And then if I go to my 60% scenario, you can look at the same thing. So if I go into my output here and then I load the same control format file, I'd be able to look at the exact same thing. Now, if I want to compare the results in Arrow, where I'm looking at my two scenarios at the same time, what I would do is go into my output control window and then go to multi-scenario and then select scenarios. I've already selected the scenarios that I want to show side by side. We'll automatically color code them for you. And then this is how you can compare all your results side by side with each other. So there's a lot of flexibility there. We do the same thing in Fathom. So in Fathom, here's my 80% efficient scenario. If I hide this and then make this a little bit larger, I have I made a control format file for Fathom as well. It's this guy. So here are the results in Fathom for the 80% efficient scenario. And then here's the 60% efficient scenario results, where if I go in here and I load the control format, I actually have two different control format files for both Fathom and Arrow, and you'll see why they're different in a sec. So here's the results, and then if I'm in the 60% scenario, I can look at both results at the same time if I want. And there we go. Now, if you have multiple monitors, which a lot of you probably do, like how I do, I can pull Fathom off into another webinar, or not another webinar, another monitor, and I can easily look at results both together at the same time. However, this is a bunch of madness just looking at a whole bunch of results in a tabular format like this. So that's, kind of confusing, and it doesn't really give a lot of good visibility as to what's going on. So what I did was I actually went in and I copied and pasted a whole bunch of data into a spreadsheet. Which, a quick aside here, if you go back to our website, aft.com, under the Learning Center, there's tips and tricks. Make sure you're paying attention to our tips and tricks page each month, because we're constantly putting out excellent new blog articles that show you how to use the software more efficiently and effectively. So if you go down here to page 2 or 3, there's a really important blog article that I want to highlight. It looks like if you were to look at this today, it's on page 3. This is the blog article that I want to highlight, the new AFT Excel Export Manager. If you were to read that blog article, it would show you how you can set up the Excel Export Manager to automatically export any number of results to a spreadsheet for you. That way you can go right into Excel. And so if you read that blog, it'll tell you how to set this up. Now, I didn't do that in my model here. I did things the old-fashioned way, where I just clicked on this column header and I did Control-C on my keyboard, and then I went into Fathom, and then I did, or not Fathom, this is Excel. And I went into Excel and I did paste. So here, this is the 80% efficient scenario, and these are the same results for AFT Arrow and the results for AFT Fathom. I also copied and pasted the results for the 60% efficient scenario. Here's my Arrow results. Here's my Fathom results. The next thing that I did was I calculated some differences. So if I go to my 80% efficient scenario, I simply calculated absolute differences and percent differences. So here for my absolute differences, for each pipe, all I did was I subtracted the two tables. So I just went in here and I subtracted the Arrow or the Fathom results from the Arrow results, because I wanted to see how much the results have changed between Fathom and Arrow. If you look at the differences in absolute terms, you can see that the differences in results are very small. Now, here's something that's different in Arrow that's not the same in Fathom. In Arrow, we calculate what the velocity at the inlet is, as well as the velocity at the outlet, and all the velocities throughout the pipe, because the gas is going to accelerate. So if I look at a certain pipe here, you can see how the velocity actually changes inside the pipe. So at the inlet, we're at 210 feet per second. At the outlet, we're almost at 300 feet per second. Fathom is not going to be able to do that because it's assuming constant velocity in Fathom. So in Fathom, all you're going to see is a straight line, versus Arrow, you'll see something that looks kind of like that. My drawing is not very good. So what I did here, in order to try and get to a point where I'm comparing apples to apples a little bit more, is in my output control format, instead of showing the inlet velocity and the outlet velocity, I went into the output control window here, and there's a parameter for velocity average. That's this parameter right here. So if you want to compare apples to apples, you'd probably want to look at the average velocities in Arrow and compare that to the velocities in Fathom that you would see. So that's why here I have in my spreadsheet the average velocity in Arrow versus just the velocity in Fathom. And you can see how the results are different there. So that compares things a little bit more directly. And then I also did a percent difference. So here you can see for pipe 2, the velocity in Arrow is different than Fathom by 41%. Now, that means that your average velocity in Fathom is about 95%, or 95 feet per second. In Arrow, it's 133 feet per second. If you were to look in the Arrow results, you'd actually see what the real velocities are, like in the axial points that I just showed you, where you see the graph accelerating. Now, these are the differences in results for my 80% efficient scenario. When you email me for my presentation, I will be happy to send you the model files as well as the spreadsheet itself. And so email me and I'll send you that in a zip folder, because I can't attach the model files like I did my PDF of the presentation. So email me and I'll send these results to you. That way you can see how different the results are. So you can see by the percentage differences, there are some significantly different results. For example, my pressure losses, you have up to 40% differences in results for pressure loss between Fathom and Arrow. But here's the thing, look at the pressure values that we're dealing with. We're dealing with very, very low pressures, really close to atmospheric, essentially. So this is where using graphs is a lot more useful. In both Fathom and Arrow, I went into my graph results window and I did 3 different parameters. So I've already created it, so I'm just loading it here. What I did was I selected a flow path from the supply end here out to discharge room A3. And for that flow path here, these are the pipes that are located in that flow path, and I'm plotting pressure, velocity, and temperature. And so you can see those graphs all stacked up in this fashion. I did the same thing in Fathom. So in Fathom, I have the same graph list item right here. So again, when you're trying to compare results between Arrow and Fathom, it's easiest to do this in graphs. So what I did was I clicked on this button to copy the XY data. I pasted it into Excel, and I modified that pasted data into these tables so that it looked a lot nicer. And these are the graphs of the comparisons. So here's the temperature profile. The blue line is the temperatures in Arrow. The orange line is the temperatures in Fathom. As you can see here in Fathom, we have a constant temperature. The compression thermodynamics in Arrow is significant. So you can see how the temperatures vary very much. So between Arrow and Fathom, Fathom is just not going to give you the right results. The temperatures very well could impact your pressure and flow distribution throughout your system. Now, if we look at other results here, here's what the velocities look like. So again, the orange line is the velocities in Fathom. The blue line is the velocities in Arrow. So take a look at this here. We see just straight lines for Fathom. That's because Fathom is doing incompressible flow, assuming your velocity is the same in every single pipe, which in reality it's not. As you can see, there's a slight acceleration in each of these different branches here. And Fathom is not doing a very good job at predicting what the actual velocities are. So here, the velocities between Fathom and Arrow are significantly different. The last thing to look at here is the pressures. So if we look at the pressures here, the pressures are actually very close to each other. So this is what can maybe give you an indication for a system like this where you're dealing with really low pressures. I'm just showing between 14 psia and 26 psia. The pressures here are very close to each other. So you have very small differences in pressure. These results that Fathom is able to predict might be okay. But again, you don't know how certain your results in Fathom would be unless you compare them to actual compressible flow methods with using AFT Arrow. And so this is where it's really important to look at things side by side. I've done the same thing with the 60% scenario. You essentially see the same types of trends. The 60% efficiency scenario basically has the biggest effect on temperature. So instead of the temperature coming out at 170 degrees Fahrenheit, we're coming out at about 230 degrees Fahrenheit for the 60% efficient scenario. But overall, your velocities are still fairly similar to what they were before, as well as your pressures. Now, let's take a look at the flow rates now. So for my flow rates, I actually have a different output file here. So what I did was I went in and I'm going to load my control format. This is Arrow with volumetric. And so the reason why I did this is because I wanted to show you the flow rate in different ways. So here I've got my flow rate in pounds per second as a mass flow rate in Arrow. In Arrow, I have the standard cubic feet per minute, and then I have the volumetric quantity, volumetric flow rate average in cubic feet per minute. The important thing that I want to note here is that your volumetric flow rate at the inlet and outlet of your pipes are different from each other in compressible flow. So here, this is why volumetric flow rate in Arrow is a bit meaningless, or for gas systems in general, because they're different from each other. So what I did was I added the volumetric flow rate average to my list of parameters. The reason why is because I want to look at these mass flow rate and volumetric quantity results and compare them to Fathom. So in Fathom, I have a similar output control format file where I have my flow rates in terms of pounds per second and cubic feet per minute. In Fathom, if you did volumetric, there is no standard cubic feet per minute. So you're limited to only doing the volumetric flow rate quantity there. I forgot to make sure that I was showing both results. So if I did this. So here's what I did, is I took these results from Fathom and Arrow, and I copied and pasted them into this spreadsheet here. So here's my pipe results, and I've got my 80% to 60% comparison for efficiencies for each of these pipes. Here's my Arrow results for mass flow rate. Here's my Fathom results for the mass flow rate. As you can see by looking at these results here, that might be a little bit too big. You can see here that the results are very, very similar for the mass flow rate quantities. So Fathom is actually doing a really good job at predicting the mass flow rate results by using incompressible flow methods for this specific system, which if you have a ducting system or a air system where you have, relatively low velocities, low pressures, and no temperature changes, then your results between Fathom and Arrow should match up pretty nicely. However, the million-dollar question is how low is too low? I mean, how significantly high of velocities or pressure losses do you have to get until your results start deviating from each other? Well, again, if you're only looking at Fathom, you're never going to be entirely sure of if your results are actually correct or not. You have to use Arrow to be able to know for sure. Now let's take a look at the volumetric quantities. So for Arrow here, I have my mass flow rate, but in terms of standard cubic feet per minute, and then I have my volumetric flow rate quantity in just cubic feet per minute. So the cubic feet per minute here for volumetric, this is the average from the inlet to the outlet. So if you compare these two results, even in Arrow, these are significantly different from each other. So the question is, which ones are correct? Well, you don't know. If I was doing the analysis in AFT Arrow, I would ignore the volumetric flow rate here. I would pay attention to flow rates in terms of either standard cubic feet per minute or normal cubic meters per hour if I was looking at a volumetric quantity. So if you're looking at a volumetric quantity in Arrow, use the ones with the word standard or normal in front of it, not just the regular average volumetric flow rate, because these are not going to be very accurate due to compressible effects. Now let's compare that to Fathom. In Fathom, these are the volumetric flow rates that you see here. As you can see, the results are significantly different. So again, which one is correct? That's the million-dollar question. If you were only looking at Fathom and you did not have AFT Arrow at the time, you would always be uncertain if these flow rates were actually correct. The main takeaway of the message here for volumetric quantities, if that's what you're looking at, is they're very different. Arrow is the best way to go. Now, if you're looking at mass flow rates in terms of pounds per second or kilograms per hour or something like that, then those would be better results to look at, not volumetric quantities. So what we can take away from this analysis that took me, 40 minutes to describe to you and probably an hour and a half on my own time to modify the models, import the model into Fathom, and then to go in and create my spreadsheet to compare results is for these two systems here, even though the temperatures are significantly different, if I wanted to be a little bit more accurate, I could use variable fluid properties. And since I know what the outlet temperature is in Arrow, I could use that in Fathom. But again, you wouldn't know if you only had Fathom. You would have no idea that that's the actual temperatures you're going to see in your system. Overall, for this particular system, because I'm modeling air and I'm only going from atmospheric pressure to atmospheric pressure, and how my flow rates of 2 pounds per second is pretty low, and how I don't have significantly high velocities. They're not very high for a gas system. My pressures are not very high. My pressure losses are pretty small. Then this might be a system where you could get away with using AFT Fathom, where incompressible flow methods might have some level of validity. But as you can see here, there is some significant differences, but you as the engineer have to determine which ones you trust. Arrow is always the ones that you can trust. Fathom or any other compressible flow correlations, you're always going to be unsure of. I wish I had time to be able to show you today, but a system that might be significantly more different would be something like this, where I have a process steam system. So for my steam system here, let me just show you this. This is again pulled from our standard examples. So if you go to show examples and pick your favorite units, it's the process steam system here. You can do the same type of analysis. So in Arrow, these flow rates are significantly high. So they are, tens of thousands of pounds per hour. I don't know what that is in pounds per second, but they're pretty, well, actually I do. If you run the model, instead of just 2 pounds per second for that air system, these are on, if I sort this from ascending order, the flow rates are different between 2.5 pounds per second all the way up to 45 pounds per second. So those are some really, really high flow rates for your steam system here. Also, if you look at the pressures, there are some significantly high pressures because we have supply pressures of 300 psia and 800 degree Fahrenheit steam from these processes. If we look at the pressure losses here, if I sort my pressure losses, I'll sort them in descending order. We have pressure differences of 87 psi all the way down to just about 0. So you have some very significant differences in pressures for each of your pipes from the inlet to the outlet. So if I was to go to my graph results window here and just do a quick plot. So I'll pick this as a flow path here. So we'll take a look at pressure, we'll take a look at velocity, and then we'll take a look at temperature. Look at that. These are some very significant changes in pressure and temperature and velocity. And so if this is the type of system that you're working with, then your answer's in Fathom. You could bring this model into Fathom and you could model it, and you're just going to see how Fathom is just dead wrong for this type of a system. So it all depends on what your system is and how high of velocities can you get until incompressible flow methods are no longer good enough. You're always going to be uncertain. That's the key thing to take away here. So whenever you're dealing with a gas system, sometimes Fathom can do a pretty decent job, like in our air system here. Otherwise, Arrow is always going to give you the best and most accurate answers. Arrow, again, will properly account for real gas effects, heat transfer, sonic choking. I don't have time to go into it today, but I do have some slides to talk about sonic choking here. So the presentation I included here will talk about that. Anyway, thank you all very much for your time. I hope that all of you have a better idea of what you can do to try and figure out how different your results are between using a compressible flow method versus a incompressible flow method or a compressible flow scenario, and to quantify the differences in results. And again, read this technical paper on our website. It will give you a much better indication on those differences, and it talks about the various traditional methods in a little bit more depth. So read that, and that'll really help you get a good understanding of compressible flow and why you want to use a tool like AFT Arrow, which is the best tool that you can find for modeling gas flow. Okay, well, everyone, thank you very much for attending my webinar today, and thank you for bearing with me as I struggled through this with being under the weather. Glad that I didn't have to have too many issues, and let us know if you have questions. You can contact us at either sales@aft.com or support@aft.com, and we'll be glad to assist you. Thank you, everyone, and have a wonderful rest of your day.